Welcome to Lesson 2. In this lesson, we're going to look at algebraic solutions to systems of linear equations in two variables. I'm going to start with the method of substitution, which you saw briefly at the end of Lesson 1. Candace is going to talk about the elimination method, and then Steve is going to summarize the methods and talk about some special cases. So I'm just going to start by working several examples. Then we'll talk briefly about when substitution is the best method to use, and finally I'll summarize the strategy. So let's start using some substitution. So here's our first system of equations. This system is similar to some of the systems we solved in Lesson 1. You can see that the first equation we have is solved for x in terms of y. So we can simply substitute the expression for x into the second equation. Let's remember what this looks like. I know that x equals 2y plus 4. I'm going to substitute the expression 2y plus 4 in for x in the second equation. So I'm going to make some room, and I'm using parentheses because I need to consider the order of operations. I'm multiplying 2 by the entire expression, 2y plus 4. Get rid of the x, move the 2y plus 4, and now I'm left with an equation in terms of y, which I can solve. So let's do it. So I'm going to start with the substitution. So substituting 2y plus 4 for x in the equation 2x minus 3y equals 8. I have 2 times 2y plus 4 minus 3y equals 8. Simplifying so that I can combine like terms, I have 1y plus 8 equals 8. Subtracting 8 from both sides, I get y equals 0. Y equals 0 is a perfectly reasonable solution to a linear equation. But I need to solve for both x and y. Remember, the solution to a system is an ordered pair that satisfies both equations. Well, I can use the expression I have here, which gives me x in terms of y, to determine x. So if y equals 0, then x equals 2y plus 4, which equals 4. So my proposed solution is the ordered pair 4, 0. Let's check it. So I'm going to check if x equals 4 and y equals 0, then, working with the first equation, I'm going to evaluate 2y plus 4. That's 2 times 0 plus 4, which is 4, which equals x, which is what I wanted. Let's check the second equation. The expression 2x minus 3y will equal 2 times 4 minus 3 times 0, which is 8 minus 0, which is 8, which is precisely what I want. So I've got the right solution, and I can just state it. The solution to the system is the ordered pair 4, 0. Let's do another example. Now in this example is a little bit different. Both equations are given in standard form. In neither of the equations is one of the variables solved for in terms of the other. But looking at this second equation, I can see that it will probably be fairly easy to solve for t in terms of w. I'm going to start there and then proceed like we did in the previous example. So solving 6w minus t equals 5 for t in terms of w, I have 6w minus t equals 5. I can add t to both sides. 6w equals 5 plus t, and then subtract 5 from both sides. So the expression 6w minus 5 is equivalent to t. Now I'm going to do the substitution. So substituting 6w minus 5 for t, I use the second equation to come up with this expression for t. I'm going to use the first equation to substitute into. So that's 4w minus 3t equals 6. Let's do it. So I have 4w minus 3 times t, which is 6w minus 5. That needs to equal 6. I now have a linear equation in one variable, which I can solve quite easily. I have 4w minus 18w plus 15 equals 6. Combining like terms, I get negative 14w, and I'm going to subtract 15 from both sides. That gives me negative 9. So I end up with w equals 9/14. I still have to determine t, but I have an expression that will give me t in terms of w. So let's use that. So if w equals 9/14, then t equals 6 times w minus 5. So I'm going to use a common denominator of 14 here. So I have 54 over 14 minus 5 is 70 over 14. And I get negative 16/14. I have a proposed solution. Now I want to check the solution. So my proposed solution is the ordered pair WT equals 9/14 negative 16/14. Now before I check this, I just want to say one thing about this ordered pair. I did not put the variables in alphabetical order in the ordered pair. And I could have done that, but I just chose not to, because in the original system, it's going from W to T, and this will just help me check it a little bit more efficiently. So let's start the check. So if W equals 9/14 and T equals negative 16/14, I'm going to check in both equations. 4w minus 3t equals 4 times 9/14 minus 3 times negative 16/14. So I have a common denominator of 14ths. So I have 36 plus 48, which is 84/14, which reduces to 6. That's what I wanted. Let me check the proposed solution in the second equation. So I have 6w minus t, that's 6 times 9/14 minus negative 16/14, which is 54/14 plus 16/14, which is 70/14, which is indeed 5. So my solution checks. Now I can state the solution to the system. So I'm going to state that over here. The solution to the system is the ordered pair 9/14, and now my t-coordinate is negative 16/14. I'm going to reduce it here when I state my conclusion. That's equivalent to negative 8/7. Let's do another example. Now in this example, we have some fractions floating around. And when we solve linear equations in one variable, we practice clearing the fractions to make the algebra a little bit easier. We can do the same thing here. What I'm going to do is I'm going to multiply both sides of the first equation by 4 to clear the denominator of 4 in the first term on the left-hand side. So I end up with a minus 16b equals 4. Fractions are gone. Let me do the same trick with the second equation in the system. I'm going to multiply both sides by 2 in this situation to clear that denominator of 2 and I'm left with a minus 10b equals 10. So now I have an equivalent system of equations that I can solve. So this new system, a minus 16b equals 4 and a minus 10b equals 10, is actually equivalent. And if I solve this system, I'll have the same solution set as in my original system. So I'm going to solve the system that has no fractions. So let's do it. So I'm going to do a substitution, and here it looks equally easy to work with either of the equations to solve for a in terms of b. So solving for a in terms of b in equation 1, the first equation, I have a equals 4 plus 16b. I just added 16b to both sides of the equation. Now I'm going to do a substitution. Substituting 4 plus 16b for a in the second equation, I have a, which is 4 plus 16b, minus 10b equals 10. So 4 plus 6b equals 10. So 6b equals 6, b equals 1. Much nicer answer than we were getting in the previous system. Now let's figure out a. I have an expression for a in terms of b that I started off with at the beginning of this problem. So I'm going to use this to evaluate a. So if b equals 1, then a equals 4 plus 16b, which is 20. So I have a proposed solution, the ordered pair 21. Let's check it. So we want to check our proposed solution, the ordered pair 21. But we need to be sure to check the solution in the original system. So I've put the original system back here so we can perform our check using the original system. So let's do it. So if a equals 20 and b equals 1, this ordered pair should satisfy both equations. So a over 4 minus 4b, this should equal 1. Let's see. 20 over 4 minus 4 times 1, that's 5 minus 4, which equals 1. That's good. Let's check the second equation. A over 2 minus 5b, that's 20 over 2 minus 5 times 1, that's 10 minus 5, which equals 5. That's what we wanted. So we have the solution. The solution to the system is the ordered pair 21. Here's another example. Now here we're going to have to work a little bit more to use the method of substitution. Remember, the first thing that we've been doing is solving for one variable in terms of the other. None of the variables here look easy to solve for. Let's look at what's going on. Imagine if I solved the first equation for x. At some point I would have to divide both sides of the equation by 2. That would give me a coefficient on y of 3/2. A fraction. Maybe I can avoid it. Let's look at the second equation. Imagine here that I was trying to isolate x. At some point I might divide by -3. Well, 6 is a multiple of 3, so I would get an integer. 42 is also a multiple of 3. The way I know that quickly is if I add the digits, 4 plus 2, that equals 6, and 6 is a multiple of 3. So 42 is a multiple of 3 as well. So I think I'm going to use the second equation to solve for x in terms of y. So solving for x in terms of y, in the second equation, I have the opposite of 3x plus 6y equals 42. I can subtract 6y from both sides. So negative 3x equals 42 minus 6y. And I can divide both sides by negative 3. I have to divide each term by negative 3. 42 divided by negative 3 is going to be a negative number. It's going to be negative 14. And then negative 6 divided by negative 3 is positive 2. So I have x equals negative 14 plus 2y. Now I'm going to substitute this into the first equation. So substituting negative 14 plus 2y for x in the first equation, I'll end up with an equation in one variable which I can solve. So I have 2 times negative 14 plus 2y plus 3y equals negative 14. So I have negative 28 minus plus 4y plus 3y equals negative 14. So I have 7y, and I'm going to add 28 to both sides because I'm running out of room. So that will give me 14, so I see that y equals 2. These problems take lots of paper. Make sure you have lots of paper to work these problems. Now we need to still determine x. So using the equation x equals negative 14 plus 2y, which is the same as x equals 2y minus 14, I can evaluate x. So if y equals 2, then x equals 2y minus 14, which is negative 10. So I have a proposed solution to check, which is the ordered pair negative 10, 2. So let's check. If x equals negative 10 and y equals 2, then we have in the first equation 2x plus 3y equals 2 times negative 10 plus 3 times 2, which is negative 20 plus 6, which is indeed negative 14. And in the second equation, we have the opposite of 3x plus 6y. That's going to be negative 3 times negative 10 plus 6 times 2, which is 30 plus 12, which is indeed 42. Our solution checks. So the solution to this system is the ordered pair negative 10, 2. Here's another problem. Again, we're going to have to work to solve for one variable in terms of the other. This time I'm just going to randomly work with the first equation, and I'm going to solve for x in terms of y. So I have the equation 2x plus 3y equals negative 4. I'm going to solve this for x, so I'm going to subtract 3y from both sides. If I divide both sides of this equation by 2, I will get a fraction, but you know, whatever you try in this case, you're going to end up with a fraction. So I just chose this because there are fractions in this problem. So now I'm going to substitute this expression for x in the second equation. So substituting negative 2 minus 3/2 y for x in the second equation, I'll have 3 times negative 2 minus 3/2 y minus 5y equals negative 25. Negative 6 plus 9/2 y minus 9/2 y. Now when I write 5y, I'm going to write it as 10/2 y because I know I have to combine like terms. So I have negative 19 over 2y, And adding 6 to both sides, negative 25 plus 6 is negative 19. Now I'm going to multiply both sides of this equation by the reciprocal of negative 19 halves. So let me just work through that because something nice is going to happen. Negative 2 over 19 times negative 19 halves y equals negative 2 times 19 times negative 19. On the left, I just get y. On the right, I have 2. So I found that y equals 2. Let me evaluate x. I'm going to use the expression that I substituted into the second equation. So if y equals 2, then x equals the opposite of 2 minus 3 halves y, which is negative 2 minus 3, which is negative 5. So I have a proposed solution. My proposed solution is the ordered pair negative 5, 2. Let's see if it checks. If x equals negative 5 and y equals 2, then in the first equation, 2x plus 3y, that's 2 times negative 5, plus 3 times 2, that's negative 10 plus 6, which is negative 4. That checks. And in the second equation, 3x minus 5y equals 3 times negative 5 minus 5 times 2, that's negative 15 minus 10, which is indeed negative 25. So even with those fractions, our solution checked. So the solution to the system is the ordered pair negative 5, 2. Now let me just say something about this problem. We were able to solve it using the method of substitution, but we introduced a lot of fractions in the problem. Candace is going to show you another method that we could use in this situation, which might be a little bit easier than substitution. One last example. Now, here, the first equation could easily be solved for y in terms of x. We've got all those decimals in the second equation, but they're pretty nice decimals. So let's work with this using substitution. So using the first equation, 2x minus y equals 8, I'm just going to isolate y. So I'll add y to both sides, and then subtract 8 from both sides of this equation. So I see that y is equivalent to 2x minus 8. This is what I'll use in my substitution. So substituting 2x minus 8 for y, I have negative 1.5x plus 0.75y, which is 2x minus 8. That should equal negative 6. Let's solve for x. So 0.75 times 2, that's 1.5x, and 0.75 times 8, that's 6. I just quickly multiplied 3/4 by 8 to get that, but you can check. Combining like terms, negative 1.5x plus positive 1.5x is 0. So I end up with this statement that negative 6 equals negative 6. Well, that doesn't really tell me anything new. I knew that already. This is an identity. And we mentioned last time that there are some special systems of equations. Some systems of equations have no solution, and other systems of equations have dependent equations, and in that situation, both equations graph to the same line. Let's see what we have here. I'm going to take both of these equations and convert the equations to slope-intercept form. I already have that for the first equation. So I have y equals 2x minus 8. This is a line with a slope of 2 and a vertical intercept at 0, negative 8. Let's look at what we really have in the second equation. So I'm going to put this in slope-intercept form. So I have negative 1.5x plus 0.75y equals negative 6. I'm going to start by adding 1.5x to both sides. Then I'm going to divide both sides of this equation by 0.75. Now, since I'm working with decimals here, I could work this out, but I'm just going to do it with my calculator so you trust my calculations here. So the first thing I'm going to do is divide 1.5 by 0.75. You should know this, but if you don't, we'll just see that it is indeed 2. So I have 2x, and now I'm going to divide 6 by 0.75. 6 divided by 0.75 is indeed 8. Look at what I have here. Both of these equations graph to the same line. Any point on that line will satisfy both equations. This is a system of equations that has an infinite number of solutions, all the ordered pairs that lie on this line. So this system has dependent equations but we can state the solution. The solution is the set of all ordered pairs that satisfy y equals 2x minus 8. So we're done with that problem. So to kind of summarize, we want to talk about when is substitution the best method. Well, we saw some situations where it was pretty easy to use, and other situations where we had to work darn hard to get our solution. So this is the rule of thumb that I use. The substitution method works best when the coefficient of one variable in one of the equations is either positive or negative 1. Let me show you some examples here. In this system, in the second equation, the coefficient of x is 1. I could easily isolate x and solve for x in terms of y, then perform a substitution. In this system, the coefficient of y in the first equation is negative 1. Again, not too much work to solve for y in terms of x. In this last system, I have no coefficients of 1 or negative 1. I'm going to have to work to solve for x in terms of y or y in terms of x. Fortunately, there's another method that might not be quite as much work. So I'm going to end by summarizing the strategy we just used in those examples. The first step is to solve either of the equations for one variable in terms of the other. Then we'll substitute the expression for the variable solved for in the first step into the other equation. It's always important to remember that you always perform the substitution into the other equation. If you go back and substitute into the equation that you started with, you're going to get something like 0 equals 0, and you won't get any further. Then you're going to solve the equation in one variable that came up after the substitution. Once you've done that, you take the value you found for that variable and you substitute it into the equation we used in step 1. This determines the value of the second variable. Finally, we always check our proposed solution and we check in both equations. And when all of that's done, we state the solution. And one of the things we need to remember is that the solution to a system in two variables is an ordered pair. Well, that ends my part of the lesson. Now Candace is going to come and show you another method for solving systems of linear equations algebraically.
In this part of the lesson, I'm going to look at more systems of linear equations in two variables. In particular, I'm going to look at the elimination method. Sometimes this is referred to as the addition method, and I'm going to do lots of examples of this. Then I'm going to go over a summary of the elimination method, and finally finish with one last example. So let's talk about the elimination method. The elimination or addition method is based on the addition property of equality. Adding equal quantities to both sides of a linear equation does not change the solution to the equation. So if we know that A is equal to B and C is equal to D, then A plus C is equal to B plus D. Notice that we've added the left-hand sides of these equations together, and we've added the right-hand sides of these equations together. So let's solve the system x plus y equals 2 and x minus y equals 4 by adding the left and right-hand sides of the equations together. Thinking of our addition property of equality, let's pretend that x plus y is A, B is 2, C is x minus y, and D is 4. If that's the case, when we add the left and right-hand sides of the equations together, we get x plus y plus x minus y equals 2 plus 4. In practice, this isn't usually how we write things when we're doing the elimination method. To make the elimination method a little bit easier, we usually work vertically. So I'll write x plus y equals 2 and then x minus y equals 4 right underneath it and do my addition. X plus x is 2x, y minus y is 0, and on the right-hand side, 2 plus 4 equals 6. So I have 2x equals 6. Dividing both sides of this equation, I can see that x is equal to 3. I'm solving a system of equations, so I should be getting an ordered pair. I have a value for x, I need to find out what the corresponding y value is. So if x equals 3, then using our first equation, 3 plus y is equal to 2. And subtracting 3 from both sides of this equation, we get y is equal to negative 1. So my proposed solution is 3, negative 1. I need to check this in both equations, though. So for my check, if x equals 3 and y equals negative 1, then looking at the left-hand side of my first equation, x plus y would be 3 plus negative 1, which is 2. Notice that's what I want. X plus y is supposed to be equal to 2, so this checks. What about the second equation? Well, looking at the left-hand side again, x minus y would be 3 minus negative 1. That's the same as 3 plus 1, which is 4. And we wanted x minus y to equal 4, so that checks as well. So the ordered pair checks in both of the equations. This ordered pair is indeed a solution to the system. So I can write my conclusion. The solution to the system is the ordered pair 3, negative 1. Let's look at another example. Let's say we want to solve the system negative x plus 2y equals 0 and x minus y equals 1. Notice if I add the left-hand sides of these two equations together, I have negative x plus x is 0, so the variable x is going to be eliminated. In my first example, the variable y was eliminated. So eliminating the x's, I'm left with on the left-hand side just 1y, which I can write as y, equals 0 plus 1 is 1 on the right-hand side. So now I have a value for y, I need to go back and solve for x. So if y equals 1, then, well, let's use the second equation this time. X minus y, which would be x minus 1, equals 1. Adding 1 to both sides of this equation gives me x equals 2. So my proposed solution is the ordered pair 2, 1. Let's check this. If x equals 2 and y equals 1, then looking at our first equation, I'm going to focus on the left-hand side again. The opposite of x plus 2y would be the opposite of 2 plus 2 times 1. That's negative 2 plus 2, which is 0. That's what we wanted. The opposite of x plus 2y equals 0. Now let's look at the second equation. On the left-hand side of the second equation, I have x minus y. So that would be 2 minus 1, which is 1. That's what we wanted, x minus y to equal 1. So that checks. So I can go ahead and write my conclusion. The solution to the system is the ordered pair 2, 1. Now let's solve the system 6x minus 5y equals 25 and 4x plus 15y equals 13. Well, adding the equations in this form will not eliminate a variable. If we add the left-hand sides together, we get 10x plus 10y. X isn't eliminated and y isn't eliminated. So let's try multiplying both sides of the first equation by 3. Why are we doing that? What happens when I multiply the left-hand side of the first equation by 3? Well, on the left I would get 3 times 6x is 18x, 3 times negative 5y is negative 15y, and on the right-hand side 3 times 25 is 75. Now I have coefficients of y in the new first equation and the original second equation that are additive inverses. Negative 15 and positive 15 add to 0. Y will be eliminated. So let's go ahead and do that. We're going to multiply both sides of the first equation by 3. So that gives me 18x minus 15y equals 75. And then the second equation is 4x plus 15y equals 13. What happens when I add? Well, on the left, 18x plus 4x is 22x. And as we planned, negative 15y plus 15y is 0, so the y's are eliminated. On the right, 75 plus 13 is 88. If I divide both sides of this equation by 22, I end up with x equals 4. I still need to solve for y. So if x equals 4, then looking at the first equation, we have 6 times 4 minus 5 times y equals 25. So 24 minus 5y equals 25. Subtracting 24 from both sides of the equation, I have negative 5y equals 1. Dividing both sides of the equation by negative 5 gives me y equals negative 1/5. So my proposed solution is 4, negative 1/5. Well, let's check this. So if x equals 4 and y equals negative 1/5, then looking at the left-hand side of our first equation, 6x minus 5y is 6 times 4 minus 5 times negative 1/5. So that's 24. And we have negative 5 times negative 1/5, so that's going to be plus 5 and 1/5 are multiplicative inverses. When I multiply those together, I get 1. And 24 and 1 is 25. That's what I wanted, 6x minus 5y to equal 25. What about the second equation? Well, looking at the left-hand side of the second equation, we have 4x plus 15y. So that's going to be 4 times 4 plus 15 times negative 1/5. So that's 16 minus 5 goes into 15 3 times, so we're subtracting 3 here. 16 minus 3 is 13. Looking at the second equation, that's good. We wanted 4x plus 15y to equal 13, so this checks. So I can go ahead and write my conclusion. The solution to the system is the ordered pair 4, negative 1/5. Now let's solve the system x equals y plus 1 and x over 2 minus y over 3 equals negative 2. Well, the first thing we want to do here is to convert the first equation to standard form. Notice that this system looks like it's set up for substitution. That is one way I could solve this, but if I substituted y plus 1 for x in that second equation, Notice there's fractions in the second equation. I'd have fractions to work with. To avoid that, I'm going to convert the first equation to standard form so that this is set up for elimination. So, starting with x equals y plus 1, I want this in the form ax plus by equals c. Essentially, I want the variables on the same side of the equal sign. So I'm just going to subtract y from both sides of the equation. That gives me x minus y equals 1. The next thing that I want to do is to clear the fractions in the second equation. My arithmetic is going to be a lot easier if I don't have all of those fractions while I'm going through the elimination process. So looking at that second equation, we have a 2 in the denominator, x over 2, minus we have a 3 in the denominator in y over 3. The least common multiple of 2 and 3 is 6. So if I multiply both sides of this second equation by 6, I'll eliminate the fractions. So I have 6 times x over 2 minus 6 times y over 3 equals negative 12. 2 goes into 6 3 times, so I have 3x, minus 3 goes into 6 2 times, so I have 2y, equals negative 12. So now the system that I have to work with is my first equation rewritten in standard form, x minus y equals 1, and my second equation with the fractions cleared, 3x minus 2y equals negative 12. Let's solve this system. So looking at these two equations, I know that if I add the equations together in this form, on the left-hand side I'm going to have 4x minus 3y. Neither x nor y will be eliminated. Since the coefficients of x and y in the first equation are 1 and negative 1, that seems like the easiest equation to focus on to decide what variable to eliminate. And either way is going to be pretty easy. If I multiply the equation x minus y equals 1 by negative 3 on both sides, then I'll have negative 3x, which is the additive inverse of 3x. Or, if I multiply both sides of the equation x minus y equals 1 by negative 2, then I'll have positive 2y, which is the additive inverse of negative 2y, and I'll eliminate the y's. I think in this problem, I'm going to eliminate the y's. So I'm going to multiply both sides of this first equation by negative 2. So this gives me negative 2x plus 2y equals negative 2. And then just writing down that second equation, 3x minus 2y equals negative 12. When I add the left-hand sides together now, negative 2x plus 3x is x. 2y minus 2y, of course, is 0. We eliminate the y's. And on the right, negative 2 minus 12 is negative 14. So I get x is negative 14. I still need to solve for y. If x equals negative 14, then looking at that first equation, we have negative 14 minus y equals 1. Adding 14 to both sides of the equation, I have the opposite of y equals 15. Dividing both sides of the equation by negative 1, I have y equals negative 15. So my proposed solution is the ordered pair negative 14, negative 15. But I need to check this. For my check, I need to make sure that I use the original system of equations. So if x equals negative 14 and y equals negative 15, then checking in my original system of equations, the first equation, x equals y plus 1, I'm going to start with that right-hand side where there's some addition. Y plus 1 would be negative 15 plus 1, which is negative 14. That's what we wanted x to be, so this checks. What about that second equation? Well, looking at the left-hand side, x over 2 minus y over 3, that's negative 14 over 2 minus negative 15 over 3. Negative 14 divided by 2 is negative 7. Minus a negative makes this plus. 15 divided by 3 is 5. Negative 7 plus 5 is negative 2. That's what we wanted, x over 2 minus y over 3 to equal negative 2. So that checks. I can go ahead and write my conclusion. The solution to the system is negative 14, negative 15. Now let's solve the system 3x equals 3y plus 15, and x minus y equals 7. Notice that once again the first equation is not in standard form. I have variables on either side of the equal sign. So the first thing that I'm going to do is take my equation 3x equals 3y plus 15 and subtract 3y from both sides. So 3x minus 3y equals 15. So now the system I have to solve is 3x minus 3y equals 15, and x minus y equals 7. If I add the two equations in this form, neither x nor y will be eliminated. If I take that second equation, though, and multiply both sides by negative 3, I'll be able to eliminate the x's. So let's multiply the second equation, both sides, by negative 3. That gives me negative 3x plus 3y equals negative 21. Then taking my first equation, written in standard form, 3x minus 3y equals 15. When I add these together, negative 3x plus 3x is 0. 3y minus 3y is also 0. So all I have left on the left-hand side is 0. On the right, negative 21 plus 15 is negative 6. 0 equals negative 6? Well, this is definitely a false statement. And if we think back to some of our work with substitution, we're supposed to recognize that this is an inconsistent system. And we saw when graphing inconsistent systems that the graphs turned out to be parallel lines. Well, you can't really check a system of equations that's inconsistent because it has no solutions by substituting the values of the variables in the equations. There are no values to substitute. What we can do is put each of the equations into slope-intercept form. An inconsistent system with no solutions should graph to parallel lines. So in slope-intercept form, we should be able to recognize parallel lines. So let's go ahead and do that. Starting with that first equation, 3x equals 3y plus 15. In slope-intercept form, I want to solve this equation for y, so I'll start by subtracting 15 from both sides of the equation. So 3x minus 15 equals 3y. Then I'll divide both sides of the equation by 3, which leaves me with y by itself on the right-hand side, and I need to remember to divide both terms on the left-hand side by 3. 3x divided by 3 is x, minus 15 divided by 3 is 5. Well, let's do the same thing with the second equation. My second equation is x minus y equals 7. Let's subtract x from both sides of this equation. So that would give me the opposite of y equals 7 minus x. And then let's multiply both sides of the equation by negative 1. That just changes the sign of every term. So we have y equals negative 7 plus x. Well, let's look at our two equations in slope-intercept form. The first one, y equals x minus 5, we see has a slope of 1 and a y-intercept of 0, negative 5. The second equation, y equals negative 7 plus x, we see has a slope of 1 and a y-intercept of 0, negative 7. So if we graphed these two lines, they have different y-intercepts, 0, negative 7 and 0, negative 5, but they're parallel. They're never going to intersect. So in this case, the system is what we call inconsistent. Which means that there are no solutions. Parallel lines never intersect. So now let's do a summary of the elimination method. In the elimination method, we want to write the equations in standard form, ax plus by equals c. Essentially what we're doing here is making sure that the variables are on the same side of the equal sign. And then sometimes we'll use the multiplication principle of equality to clear the equations of fractions or decimals. This just will make our arithmetic easier in our solving process. When necessary, we're going to multiply one or both equations by a number or numbers so that they have a pair of terms that are additive inverses. When we add the sides of the equation, we'll eliminate one of the variables and solve for the remaining variable. Then we'll use substitution to find the value of the other variable. We always want to check our solution in both equations, and that is the original equations, and then we'll write our conclusion. So now let's look at one last example. Let's solve the system 0.8x plus 0.3y equals 5.3, and 0.3x minus 0.2y equals 0.2. I see all kinds of decimals in the system, so the first thing I'm going to do is clear the decimals from the equations. Looking at the first equation, I could multiply both sides of this equation by 10 to eliminate the decimals. Doing that gives me 8x plus 3y equals 53. Now looking at the second equation, I could also multiply both sides of the second equation by 10 and eliminate the decimals. So this gives me 3x minus 2y equals 2. Now if I tried to add the equations together in this form, neither x nor y will be eliminated. So let's think about what we could do to eliminate either x or y. Well, looking at our second equation, there's not an integer I can multiply by 3 to get 8. And there's not an integer I can multiply by negative 2 to get 3. This is one of the systems I'm going to end up multiplying both equations by a number in order to eliminate one of the variables. I'm going to go ahead and focus on the variable y since one of the coefficients is positive and one's negative. So then all I have to do is focus on the absolute values of these numbers. So if I multiply the first equation by 2, my coefficient of y will be 6. And if I multiply the second equation by 3, my coefficient of y will be negative 6. Those are additive inverses. So I'm going to take 2 times 8x plus 3y equals 2 times 53. And I'm going to take 3 times 3x minus 2y, which will equal 3 times 2. So the first equation becomes 16x plus 6y equals 106. And the second equation becomes 9x minus 6y equals 6. Now if I add these equations together, on the left-hand side, 16x plus 9x is 25x, 6y minus 6y is 0, and 106 plus 6 is 112. Dividing both sides of the equation by 25, I have x equals 112 over 25. I still need to solve for y. So working with x equals 112 over 25, generally we would tell you to leave your answers as fractions. Most math teachers like to see fractions for answers. But remember, our original system of equations had decimals. What I'm going to do is pull out a calculator and see if 112 divided by 25 is a terminating decimal. If the decimal does terminate, I'm going to go ahead and write the value of x as a decimal. Again, I'm only doing that because the original system of equations had decimals. So I want to take 112 and divide it by 25. It is a terminating decimal, 4.48. So I'm going to go ahead and rewrite 112 over 25 as 4.48. Now I'm going to solve for y. I think I'm going to use that second equation just because it has some smaller numbers in it. So if x equals 4.48, then looking at the second equation, we have 3 times 4.48 minus 2y equals 2. Well, let's get out a calculator for that first calculation. So I want to take 3 times 4.48, that's 13.44, minus 2y equals 2. Then I need to subtract 13.44 from both sides of the equation. That gives me negative 2y equals negative 11.44. Then I need to divide both sides of the equation by negative 2. So y is going to be positive, and let's see, 2 goes into 11.44 how many times? 2 goes into 11 5 times. 2 goes into 14 7 times, and 2 goes into 4 2 times. So 5.72. It looks like my proposed solution is the ordered pair 4.48, 5.72. But I need to check this. Notice that I'm back to the original system of equations, the system of equations that had decimals. Whenever you're checking your answers to systems of equations, you want to check with the original equations in the system. You might have made some arithmetic errors when you did some conversions. So if x equals 4.48 and y equals 5.72, then looking at our first equation, just focusing on the left-hand side, 0.8x plus 0.3y would be 0.8 times 4.48 plus 0.3 times 5.72. And I'm going to pull out a calculator for this check. So I need to take 0.8 times 4.48 plus 0.3 times 5.72. That equals 5.3. Looking up at the first equation, that's good. I wanted 0.8x plus 0.3y to equal 5.3. But I still need to check in the second equation. So looking at the left-hand side of that second equation, I have 0.3x minus 0.2y. So that would be 0.3 times 4.48 minus 0.2 times 5.72. And again, I'm going to pull out a calculator. So I have 0.3 times 4.48 minus 0.2 times 5.72. And that equals 0.2. This is good. Look at the second equation. I wanted 0.3x minus 0.2y to equal 0.2. So my solution checks. I can go ahead and write my conclusion. The solution to the system is 4.48, 5.72. And now I'm going to turn this over to Steve, who's going to look at some more systems of equations in 2